Okay, so we've already looked at the case where we take two sets in a bracket, for example, A and B, and there's something between them, whether it's a union or it's an intersection or whatever it may be. However, from this set, we subtracted another third set, like C. And we found that the C can actually go into the brackets, and we end up getting that that's the same as saying A minus C, union or intersection with B minus C, right? The C minus C can be applied to A and to B, and we can keep the thing in between them. However, what if, like in this case, we flip the order? What if instead we first take our distinct set, or not distinct set, our one set, and subtract from it a bracket with two sets that are somehow related to each other? Okay, well, that'll give us a question that looks like this. So how do we know if this is going to be true? Well, let's draw some diagrams, right? Let's take the case where we have the three sets like so. Maybe I'll actually draw them a little bit bigger. So we take our three sets like so. We have this represent the left-hand side and this represents right-hand side. And all we have to do is shade in the areas that the left-hand side is interested in and see if that's going to be the same shaded area the right-hand side is going to be interested in. Well, let's see. So what does B intersect with C? Well, B intersect with C is going to be this area shaded in blue. Okay. And then we want to take the entire set A and subtract from it this shaded area of B intersect with C. So that means we want to highlight all of A that does not include the areas of A that are in the blue part. So that means we're not going to shade in this part because this part is an A, but it's part of the shaded region we don't care about. Okay, so we're actually interested in this orange section right here. Are we going to find that the right-hand side is going to be interested in the same orange section? Well, let's have a look. The right-hand side, we know, is going to be A minus B first. So what is going to be A minus B? Well, A minus B, and maybe I'll select a different color. I'll select this blue. A minus B is going to be everything in A that's not also in B. So it's going to be everything in A like so, like this. And we're not going to shade these two regions because they're also part of B. That's what A minus B is. So we know that this is going to be A minus B. So we have this part taken care of. Maybe I'll actually highlight the left-hand side as well so it's a little more clear. Okay. And then what about the other bracket on the right-hand side? A minus C. Well, A minus C, maybe I'll find a better marker. Give me just one moment. Well, A minus C is going to be everything in A that's not going to be in C. So we want to shade in everything in A that does not share anything with C. So that means we're not going to shade in these two regions because they're a part of C. And I kind of went over the line a little bit here, so maybe I'll fix that. Like so. So there we go. Okay, and then we want to look at the intersection between our red and our blue. So which regions have both red and blue? Well, we know that we're not going to be looking at this region because this region only has red. And we're not going to be looking at this region because this region only has blue. So we're only going to be interested in this region here because it has both colors. Or more obviously, let me highlight that in orange, what I'm talking about. Okay, so there we go. Note that the orange area on the right-hand side is not the same as the orange area on the left-hand side, because the left-hand side includes these two regions right here in purple. However, on the right-hand side, these two regions here are not included. So in one case, we are including them. In the other case, we're not including them. This means that these two sets on the left and the right have to be different. So that means that this statement is going to be false. So now let's go ahead and prove this. So in order to prove a statement is false, we have to write out the negation of this statement and prove the negation is going to be true. So what is the negation of this statement? Well, we know that this is a for all statement because we're looking at any sets A, B, and C. For all sets A, B, and C, because they have no restrictions, it could be any of the sets can be anything, right? So this means that we're looking at a for all, which means the negation of a for all is going to be a there exists. So that means our proof is going to start with proving the statement that there exists. Now, what does there have to exist? Well, it's a for all for all sets A, B, and C. So it means there have to exist sets like this: sets A, B, and C. And what are we trying to prove? Well, we're trying to prove they're not equal to each other. So we have to find three sets where A minus B intersect with C is not equal to A minus B intersect with A minus C. So this is actually what we're going to prove instead. Now, how do we prove something is not equal to something? Well, we simply have to understand, what does it mean for something to be equal to something? Well, for something to be equal to something, it means that everything on the left-hand side has to be on the right-hand side, and everything on the right-hand side has to be on the left-hand side. So that means originally, if this was true, it would mean that A open bracket minus open bracket B intersect with C is a subset of the right-hand side, A minus B intersect with A minus C. And similarly, at the same time, A minus B intersect with A minus C is a subset of A minus open bracket B intersect with C. Both of these would need to have been true for the blue statement to be true. But because we've already seen visually that this is not true, it means that for this to not be equal, it must be that one of these is not true. So it could be either that this is not true, or we can show that this is not true. It's sufficient to show one of them. I think I might do both, just to be really thorough and explicit. But in reality, if you can just show one of these is not true, then we already know they're not equal. One might be a subset of the other, however, they will not be equal. So how are we going to know which one we're going to not prove? Well, after some more thought, let's redraw them, right? So here we have our two sets. We have the set on the right over here and the set on the left over here. Let me quickly label our sets. Well, is one a subset of the other? And the answer is yes. Notice that the right-hand side, everything here, everything shaded here is going to be here, right? Because this entire area appears here. However, the other way is not true. This is not going to be a subset of the right-hand side because there are some sections, like these two sections, that are here that are not in here. This means that when we want to prove that this is false, we cannot prove that this is false because we know that this right here is going to be true. We can see that everything on the right-hand side is in the left-hand side. This shaded area is in the left-hand side, which makes the right-hand side a subset of the left-hand side. However, we notice the left-hand side, not every shaded area here can be found here, which means that we're actually going to be proving that this part is not true. And it's going to be this statement that we're going to prove is not true that's going to show us that that is not true. So let's go ahead and start writing that. Okay, so when looking at this left-hand side, we need to think of creating actual sets where when we look at this, this is not going to be a subset of that. So what does this mean? Well, what regions do we know are in here but not in here? Well, we know that it's going to be these two regions. So this means that we have to think of a set A, B, and C such that when we have this relationship, there's going to be elements here. However, with the same three sets, when we have this relationship, those won't be there. So what does this mean? Well, let's label this, for example, anything. We can label this 1 and this 2. Okay, what does it mean for 1 to be in this region? It means that 1 must be an element of A intersect with B. What does it mean for 2 to be in that region? Well, for 2 to be an element of that region, it must be that 2 is an element of A intersect with C. Okay, so what does this tell us? This tells us a set of rules our three sets have to follow for us to show this. Well, what does it mean for 1 to be an element of this? It means that 1 must be an element of A and 1 must be an element of B. Okay, fantastic. What does this mean? Well, this means 2 must be an element of A and 2 must be an element of B. Great. So actually, this is more than enough information we need to create our sets. So what does A need to have? The set A has to have 1 and it has to have 2. So A is going to have 1 and 2. What does B need to have? Well, we know B needs to have 1, and it can have anything else, but all we care about is 1, and we want to keep the example simple. Okay. And this is not supposed to be B, this is supposed to be C. My apologies. And what does C need to have? Well, C definitely needs to have a 2, so we're just going to leave it like that. So there we go. We've created our 3 sets that are going to be serving as our examples here. Let's just verify that they do in fact show us these two are not equal. So if we were to follow A minus B intersect C, what are we going to find? Okay, so let's follow this. What does B intersect C? What do B and C share? Well, there are no elements B and C share, so that means that B and C actually share nothing. They share the empty set of nothing. So this ends up becoming A minus the empty set. And what do we know? I've already made a video proving A minus the empty set is just going to give you back your original set A. So that's what we know the left-hand side must be. Okay, what about the right-hand side? Well, when we take A minus B intersect with A minus C, what will we find? Okay, well, A minus B means we want every element in A that's not in B. So what elements are in A that are not in B? Well, we can't have 1 because 1 is in both A and B. However, 2 is in A, but not in B. So that means that this actually becomes the set containing only 2, okay? And then what is A minus C? Well, A minus C will be 1 because A and C both share 2, so we don't want to care about the 2. However, 1 is an element that is in A, but not in C. So that's what we get down here. And what do we find? Well, we're looking for the intersection between the sets 2 and 1. Well, 2 and 1, well, the sets containing only 2 and the set containing only 1, they don't share any elements, right? Because the element 2 is not equal to the element 1. So this means that this ends up becoming the empty set, or this ends up becoming 2 intersect with 1, which is going to equal the empty set. There we go. So we know the right-hand side is actually going to give us the empty set following this structure from our 3 sets. And what do we find? Well, if the left-hand side is equal to A and the right-hand side is equal to the empty set is not equal to A because A clearly has elements, right? We know this is not true because 1 can't be an element of the empty set and 2 can't be an element of the empty set. Okay, so there we go. We have found an example where there are elements in the left-hand side that are not elements of the right-hand side, which makes the left-hand side not a subset of the right-hand side. Now let's put all of this into actual words. Okay, so let's begin by creating our 3 example sets. We will say, suppose A is the set containing 1 and 2, B is the set containing 1, and C is the set containing 2. Fantastic. We can then say, then A minus open bracket B intersect with C is going to equal to A minus the empty set. And we can put in brackets since 1, or I guess we could say since B and C have no elements in common. Fantastic. And we could say then A minus the empty set is equal to A. Now you would probably want to prove this as well. However, I've already proven that in a separate video, so that's why I'm just going to assume that we can just make that statement. So there we go. Fantastic. So we found out what the left-hand side is equal to. Great. Now, what can we show? Well, we can then show that on the other hand, now we look at the right-hand side, A minus B intersect with A minus C is going to equal to, well, we could just maybe claim this to be, we can claim this to be the set 1 and 2 minus the set of, what does B have? B has 1, in a bracket, intersect with the set containing 1 and 2 minus the set containing 2. Fantastic. And then we can make an arrow, and we could say that then this would simplify to, obviously, the set just containing 2, intersect with the set containing only 1, which is going to equal the empty set since, empty set since the set 2 is not equal to the set 1. I think that's more than enough. Okay, fantastic. There we go. And what do we notice? Well, we notice that therefore A minus B intersect with C is equal to A, which is equal to, which is going to not be a subset of the empty set, which is going to equal to A minus B intersect with A minus C, since A contains the elements 1, or we can just use one example, right? We don't have to claim both 1 and 2. We can just say since, we can say 1 is an element of A, but 1 is not an element of the empty set. So there we go. We can now say that making the negation true, showing the original statement to be false. Okay, we have now shown that this is not going to be true.